So, hello everyone, welcome back. And today we'll be looking at hydrogen bonding in AS chemistry and just how it's formed, when it forms, and the different properties of water along with it. So, hydrogen bonding is the strongest type of intermolecular bonding. So, we looked at last video, we looked at the two different types of bonding there is. There is ID bonding, which is instantaneous dipole to induced dipole, and there's another one called PD, which is permanent dipole to permanent dipole. So, these are basically formed between polar compounds, while ID, instantaneous dipole, and induced dipole are formed between all compounds. So, hydrogen bonding is just basically another type of PD force, but it occurs with hydrogen only, and it occurs with only a few elements. Okay, so when does hydrogen bonding take place? Hydrogen bonding can occur when two of these conditions are met. For example, when there's a species, so an atom, which is very electronegative. As we know, NOF, nitrogen, oxygen, fluorine, are the three most electronegative elements. So whenever a hydrogen is bonded with these, it will be very electronegative. It will have a hydrogen bond. So let's take an example of water here, right? We have two hydrogens and there's a water, and there is two lone pairs, since we also need a lone pair. Now imagine another water. We can take it as hydrogen, oxygen, and then we have the two here and two here. So obviously, oxygen is very electronegative, so it will pull the electron towards itself. So this will become a delta negative and this will become a delta positive. The same will happen here, negative, and this will become delta positive. Now here, what will happen? There is a hydrogen which is very delta positive, so it is not able to pull the electrons as strongly. So this is basically almost become a positive ion. So this forms an attraction between the lone pairs of the oxygen, which is very delta negative, to the hydrogen, which is delta positive. So this is a hydrogen bond, and it can also form between species which have a alcohol group and an NH group. So if we imagine methanol, COH, with this, and this, then oxygen obviously again will have two lone pairs of electrons, and it will become delta negative, and the hydrogen will become delta positive. And now if we imagine another methanol here, oxygen and hydrogen, this will also become delta positive, this will become delta negative. So the same thing will occur here. The hydrogen will form a hydrogen bond, the lone pairs of this oxygen. So how many bonds will form when a hydrogen bond occurs? So let us take the example of ammonia first. Over here there's three hydrogens which are all delta positive, and a nitrogen which is delta negative with two lone pairs. As we looked at, we must have at least one lone pair. Now the ammonia will also be the same. Hydrogen will be delta positive and the nitrogen will be delta negative. So again, what will happen, like we know, the delta positive, since hydrogen is such bad at attracting the electrons, nitrogen takes most of them and is such a strong charge that there will be a hydrogen bond between here. However, since there's only one lone pair of electrons, only one bond can form. One hydrogen bond will be able to form. However, since let's take the example of water, oxygen, like we know, has two lone pairs. So what will happen? The delta positive hydrogen of water will form a hydrogen bond between them. So this will form two hydrogen bonds per water. This will mean hydrogen has two bonds, and ammonia will only have one bond. So water will have a stronger attraction. So let us learn about the different properties of water which is caused by the hydrogen bonding. Well, we can easily explain this: high melting and boiling point. Like we know, water forms two hydrogen bonds with every other water. Each water will form two hydrogen bonds, and as we know, it is the strongest type of intermolecular force and is stronger than permanent dipole to permanent dipole, since it's a type of it. So this will obviously have very high melting and boiling points. Now let's look at the enthalpy of vaporization. This basically means the amount of energy you need to vaporize a compound, right? So normally when we're going down the group, it will increase the enthalpy of vaporization, right? This is because there's obviously more electrons are being added, and what do we know when more electrons are added? There'll be more instantaneous dipole to induce dipole forces. But why is the property of water, why is the vaporization of water 3 times as much higher? Well, we can see obviously because they're hydrogen bonds, and hydrogen bonds are permanent and the strongest type of intermolecular forces, so it obviously require more energy and is not present in other hydrides. So, high surface tension finally. Why does water have a high surface tension? Let's take this example, a very good example. I have a water on the surface, but it is also forming hydrogen bond between this water. There's one between this water. There's one between this water, this water, this water. It is forming hydrogen bonds. All the water near the surface are forming hydrogen bonds with the ones inside it. But the ones which are in the center, they're being pulled from all directions. They will have equal amounts of hydrogen bondings. They're being in all directions. So this will cause the surface tension to increase. It's basically the ability of a liquid to resist the external forces. So it won't be affected. Imagine you take a drop of water and you put your hand. If you see, at some point you're not going to be able to enter the water, but as soon as you put enough force in, it will break and it will go through. And because of these hydrogen bonds, these are so strong, the water has such a high surface tension that it doesn't easily let it penetrate the force to break. So it has a very high surface tension compared to other liquids. Finally, the most confusing property, I believe, so please pay close attention, is the density. How does hydrogen bonding affect density? In normal cases, solids are more denser than liquids, which is always true because solids are packed closer together than a rigid structure. However, this is different in water molecules. Over here, we can see the water molecule forms a lattice, like we know, it forms a rigid lattice with hydrogen bonding between them, right? And the method of the lattice forming in ice, it is very long bonds. And since the length of bonds are longer, that means they'll be further apart, right? The ice will be further apart, which will mean it will take up less mass in the same amount of volume. And over here, you can see from the structure, the way ice crystallizes, the way ice is formed and is solid, there's huge gaps in the middle. Over here, we can see, right? There's very large gaps in the middle, which causes it to have a very low density. Sometimes what I find confusing is why water? Why water, right? Why not in liquid form? Why is it less? Why is it still more dense? This is because in liquid form, the molecules are free to move, right? The hydrogen bonds will be forming and breaking. So the water are moving since they have thermal energy, since there's kinetic energy, right? They'll be moving each other faster and they will form a hydrogen bond here, but then the water will move away and the bond will break. Okay, so what will happen? It will keep on forming bonds with other waters, but it's not a rigid structure. It is not a rigid because it keeps breaking away, going away, right? It keeps breaking, so it's not a rigid structure. So this is the reason why it has a higher density, because it can keep moving together instead of having to be stuck in this very spacious lattice. So that is hydrogen bonding, everyone. Thank you for watching.